record. Okay, well, the next talk is Dick Flagg and Wes Greenman will be talking about the basic radio Jove kit hardware. So this is a part of the introduction. And for this one, because there's a couple of speakers speaking, we kind of prefer that we save the questions till maybe the end on this talk. Ready?
Thanks, Chuck.
Okay.
Well, I guess as you've heard, I'm Dick Flagg, and I designed the Jove receiver. I'm just curious, how many of you have built or operated a Jove receiver? Can I have a show of hands? Great. So that's about half of you. Here's another question. A lot of us on the Jove team have cats. How many of you are cat people, and how many of you are dog people? Okay, cat people first. Okay, dog people? That's kind of 50-50 or 60-40 for favorite cats. I just wondered if there was some relationship. Okay, we're going to talk about the radio telescope, which is made up of the receiver and the antenna, and then Jim Scott will talk about the software aspect of it. So I'll be talking about the receiver, and then Wes will tell us about the antenna. Before we get right into the receiver, though, I've had a question several times. Why do you guys operate at 20 megahertz? What's so magical about that frequency? So I can figure out how to move to the next slide. Jupiter's spectrum is such that as you go higher in frequency is plotted along the x-axis, and signal strength or power from Jupiter is plotted on the y-axis. As you go higher in frequency, Jupiter gets weaker and weaker and weaker, and it's never heard above 39.5 megahertz. Below about 15 megahertz, depending on where you are in the solar cycle, the ionosphere tends to block extraterrestrial signals from getting down to the surface. So that set the limit for us between, say, 15 and 40 megahertz, and we kind of picked 20. If you go below, as you go to a lower frequency, the antenna and the length gets longer, dipoles get longer. So if we want to go lower in frequency where Jupiter's a little bit stronger, but the galactic background is a little bit stronger, we need bigger, longer antennas. You guys will need a bigger backyard. If we go higher than 20, then Jupiter's getting weaker. So we need more antenna, more dipoles. They might be a little shorter, but you need more of them to make up for the loss of gain. So 20 was a pretty good compromise. And also the fact that one of the Jovian sources doesn't, the IOC emission region doesn't emit much above 22 megahertz or so. So that seems to be a good choice. Well, the radio telescope kit comprises the receiver, all of its parts and pieces, the manual, which was as much of a pain to develop as the receiver was fun. Of those people that have built the Jove receiver, has anybody read the manual? Right. And then the antenna, the wire, the insulators, the coax, and so forth. The person putting it up, of course, has to provide the poles. Then we have the software licenses for SkyPipe and Radio Jupiter Pro, and that's a really important part of it, is to understand and be able to operate that software. Radio Jupiter Pro allows you to predict when Jupiter will be emitting or may be emitting. We also have the reference CD that Jim Tiemann mentioned. Hopefully fairly good documentation and text support. And Jim Tiemann mentioned the fact that we've had telecons every 2 weeks since 1999. It's a lot of man hours keeping this program running, and just coordination time and and try to make sure that we're taking care of people's issues that they might have. Okay, so let's get into the receiver itself, which I guess most of you are familiar with. We're on the PC board itself, and the receiver design have stayed the same since it was first developed. We're up onto revision E on the printed circuit board, and hopefully it's getting a little bit easier to stuff. The front panel looks a little bit better. We used to, those of you that started off in this program in the early days, there was one of these terrible adhesive decals you had to stick on the front that always went on crooked. So we've got the front panels of the receivers painted now, and then the Jove manual itself, which we've been working to improve and incorporate better troubleshooting procedures and just generally make it a little more readable and easy to work with. So I'm going to go through a block diagram of the receiver. I guess if I figure out which button to push, it'll do better. Okay. Well, it'll flow down from the top to the bottom here. It's a 20.1 megahertz receiver that you can tune over a couple of hundred kilohertz. Start out with some bandpass filtering, a preamp, the local oscillator, and mixer. It's a direct conversion receiver. That means we take the radio frequency and convert it directly down to audio. There's no detector as such. It's just a question of shifting a little chunk of the radio spectrum down to audio so you can hear it and then feed it into your computer. There are two parts in here. One is the local oscillator. That's a generator inside the receiver that generates a sine wave at around 20 megahertz, wherever you tune to. And then there's the mixer, which takes the incoming radio signal and beats it against that local oscillator frequency, and you get sum and difference frequencies out of that. I know a lot of you guys know all this stuff, but I want to kind of cover some of the basics here. So that the outputs of that mixer then is in the audio range, and then we filter that to knock out any interfering stations that are a little outside the band that we want to tune, and the rest of it's just an audio amplifier, and we come out to two outputs. It's enough audio power to drive the pair of headphones, but not a loudspeaker. So you have to use an amplified speaker. There's also a 20 megahertz crystal test oscillator built into the box to allow you to align the receiver so you don't need any other test equipment. There's the receiver schematic, I don't know, 100 parts, 3 transistors, 3 ICs, a bunch of diodes and capacitors and inductors, all the stuff you guys like. I stripped off the power distribution. Do I have my water over there? Which one? This one? Okay. It's strange, it's like a desert up here, just dry. Okay, so I stripped off all the power distribution stuff just so you can follow the signal flow through the receiver. So we start up here, bless you, start up here at the antenna and go through a little bit of impedance matching and filtering into a JFET transistor to amplify the signal. And then we go into the mixer and local oscillator. The T's on here, these are the elements that are adjusted when you set the receiver up. Just after you build it, you have to go through a little calibration. The frequency is determined by that pot on the right-hand side of the radio, and that generates a different DC voltage, which goes to a device called a Vericat. And it's a diode whose capacitance changes with DC voltage. So between the varying capacitance on VD1 and the inductor in parallel with it, you've got a tank circuit, and that controls the frequency of the local oscillator, the LO. And get the mixing action in the SA602. And then we go into a low-pass audio filter, and the rest of it is just going out through the audio amplifiers to make the signal loud enough where you can hear it and do something Well, receiver performance specs. In order to afford the receiver, we had to make it as cheap, inexpensive as we could. And to do that, we really had to be careful about not making it do things it didn't have to do, but making sure that it worked well enough to do what it was designed for, and that was to listen to Jupiter. So there are a lot of specifications that receiver designers worry about, and this is kind of a list of them, some of them here. We're going to talk about most of them in probably nauseating detail in just a minute, but I'll just say a word about automatic gain control. This is a circuit that's found in most commercial receivers, ham radios and transceivers. It kind of keeps the volume on the output more or less constant, so you can listen to a weak distant station or a local station, and they both come out at the tail end about the same strength. You don't want that in a radio astronomy receiver, because you get a nice solar burst and it tries to build up, and the AGC circuit grabs it and pushes it right back down, so you don't hear anything. Or it will modify the shape or structure of a Jupiter burst. So I think we've heard the question, can I use my ham radio transceiver or receiver? Yeah, if you turn the AGC off, it will probably work, although sometimes that switch is a little misleading, and also on some receivers, even though it says in the software that you turned it off, you didn't. We used to use Collins 75S1 receivers at the Observatory, and Wes had to go in and make considerable modifications to the receivers to get the AGC completely removed from the radio. And let's see. One other thing I wanted to mention before going through the technical specs of it was an attempt to make the kit reasonably easy to assemble, not using any surface mount parts, and keep the cost under $100, as Jim Tiemann mentioned, and then there was tech support. And this is, I think, something that's really important. The Jove team has worked very hard to provide tech support. We're always working with a few people on email, trying to solve problems. We're available, to talk with on the telecons, which we hold observing and technical telecons every few months, so that people can get on and chat with us if they're having any difficulties. If somebody just cannot get their receiver going, Wes and I will fix the radio for $25 flat fee. And I guess maybe one of the more important things, we do have a toll-free phone number to the India technical support. Well, maybe I was kidding. Okay, noise figure. I'm not going to get into too much detail on this, other than the fact that noise figure is a measure of how much noise the radio itself generates. And that's not noise you want. Ideally, the radio wouldn't generate any noise. And so all the noise coming out of the back end of the radio would be due to what was coming into the radio from the antenna. But all radios generate a little bit of noise, and what we wanted to be sure was that when you hook the antenna to the radio, that the noise came way up, that the radio didn't contribute very much. The thing that sets the background level is the noise from the galaxy itself. There are relativistic electrons spiraling in the galactic magnetic field. And that generates a pretty high level of radio frequency noise. So that's the noise floor. That's what we're going to hear Jupiter and the sun rising up above. And we want to make sure that the receiver itself doesn't contribute very much to that. So in terms of noise figure, anything under about 9 dB is acceptable. That means the receiver would only contribute about 1/10 of the total amount of noise that we're getting. In fact, the Jove receiver noise figure is about 6.5 dB. So when you hook the antenna on, you get about a 15 dB rise in noise. So you can forget about the noise figure pretty much with the Jove receiver. You guys at higher frequencies and hydrogen line That's one of your big concerns in life, is keeping the noise figure low, but not at this end of the spectrum where the galactic background is so hot. This is a typical record of after you've got the antenna connected, you see some stations. When you disconnect if you disconnect the antenna, the baseline would drop all the way down close to zero on the sky plane. And there's some lightning crashes and static and the almost inevitable power line buzz, at least if you live in Hawaii, that's the case. Tuning range, this is a plot of tuning knob position, 1 through 11 or whatever, and the frequency of the receiver. So it's pretty linear tuning. These are 3 different receivers we tested over a range of about 300 kilohertz. Gives us enough tuning range to get away from stations because you want a clear spot to operate. Frequency stability. Well, a ham radio, you need 10 hertz or better frequency stability. Jupiter is 100 kilohertz wide signals. The sun is megahertz wide signals. Jupiter is often a few megahertz wide. So we don't care so much about frequency stability. In fact, when you tune the radio, if you get your hand in there near the local oscillator, you can hear the thing swinging around if you're listening to the tone. So the frequency stability was not a real driver. The only time it's important is if the receiver's unattended. This is a plot. We hooked a SDR14 up to the antenna terminal of the Jove receiver. There's a fair amount of the local oscillator leaking out of the front of the antenna port of the radio. And just measured the frequency after the receiver was turned on. This is 2.5 hours. And frequency plotted along here. So after 15 minutes or so, the radio settles down and it'll wander a little bit, kilohertz per degree centigrade, something like that. Yes, sir. 5 minutes. Okay, I better speed up. Keith Paella operated his radio remotely and was very concerned about temperature drift because you'd walk away from the radio and then it would drift onto a station and you'd be stuck listening to a station and couldn't hear anything else. So he ran a test, and this is a curve that he generated. This is temperature in degrees centigrade versus frequency, and you can see there's quite a bit of drift. And he worked out some methods to try and tame the frequency drift on this. Actually, I think he kind of cooked it pretty well done because you notice the temperatures run from 45 to 65 degrees centigrade. It's maybe a little hotter than my shack. But this is very interesting data to us. Dynamic range is the range from the noise floor up to the maximum amount of signal that the receiver can tolerate. And again, before the receiver goes into compression, up in here the radio just can't put out any more noise, no matter how strong the signal is going into it. So what do you need? Well, if you're using a Jove antenna for Jupiter, you need maybe a 20 dB, factor of 100 dynamic range, and for the sun about 40 dB. So that was kind of one of the design criteria that we used. The dynamic range of the receiver is determined by where the volume control is set. If you set it full on, then it's not going to accommodate as wide a range of signals as it would if you set the gain control back at 12 o'clock. So this is the 12 o'clock position, and we've got a full 40 dB of input range that we can accommodate. Gain stability, radio astronomers like a nice flat line. They don't want the thing to be drifting all over the place in terms of gain with temperature. And this 30-minute run shows that we have about a tenth of a dB or less of fluctuation. So those are the technical specs for the receiver. And you can read what they are. We've kind of talked about each one of them. I think maybe the most important aspect of the receiver is the following non-technical spec. It works. Thank you very much. Wesley, your turn. while Les is getting set up here, Wes is the one that puts all the parts together and makes sure that we get good kits when they're sent out to be built. And he tests every one of the integrated circuits to make sure those are good. So this is the guy that is a big contributor to the success of the kit.
Yes, my name is Wes Greenman. Little memory problems I have to use cheat sheet notes, unlike the rest of the crew. I'm not used to an audience of this size. Usually, where I live, audience of 4, all female, my wife and 3 cats. So, so you're a big change. So forgive me if I'm a little nervous. The first slide is the Jove array in my backyard, the radio Latitudes outside, and you can not see my antenna pretty well. The dipole wires are pretty much invisible. We're going to talk about the antenna gain, and we're going to talk about what is an antenna. So what is an antenna? A lot of definitions. I discovered not just one definition of an antenna, there's a lot of them. But one definition would be that the antenna is a device for converting electromagnetic radiation in space into electrical currents in conductors. And you're surrounded, as you know, by antennas all over the place, right? CB antennas, microwave towers, AMF antennas, and the old, CB antenna, which is kind of one thing of the past, I think. And there's several terms you need to kind of understand when you discuss antennas. One of them is being used the term DBI. To define an antenna, the gain of an antenna system relative to an isotropic radiator. What is an isotropic radiator? That little dude right there, it's a definition is the theoretical point source of electromagnetic energy which radiates intensity in all directions. You kind of look at it as a very large unity gain balloon. And if you take, for an antenna to have gain, which I'm going to discuss in a minute, take that round isotropic, you kind of squeeze it, you get gain in a certain direction, as on the right image up there. That's what we're after. And the definition of gain would be, as Dick points out, you take a cheerleader's megaphone, stick it in your ear, which is kind of silly looking, but basically it amplifies sound from a certain direction. And kind of an antenna is the same way, where it doesn't amplify sound, but it amplifies a radio signal given from a certain direction. And that's what we want in an antenna. We want to the right image up there where that antenna now has gain. It's all referred to the isotropic, so DBI. And then Jupiter, for Jupiter, of course, Jupiter takes several, and we have a really wide beam for the antenna, so it takes several hours for Jupiter to pass through the beam. We center the Jupiter up on the mid part of the beam. Do a little bit of next slide. A little bit of math here. I'm not going to go into details, but in general speaking, you can say in any antenna, the higher the gain, the larger the effective area, and the narrower the beam width. Because if you want to collect lots of say rain, you need a big bucket, right? And for an antenna, you need to have you want to collect lots of signals. You use an antenna with a high gain and a large collecting area. And you'll notice up here, the effective area of a half-wave dipole is about half wavelength by a quarter wavelength. That amount of area in the field is significant to the antenna. In fact, that amount of area, if you had poor ground, you might want to improve the ground in that respect. For most of us, like in Florida, we don't worry about that. It's all good. You don't have to put it down to ground plane. And also, that means the effective area of a half-wave dipole is about a quarter wave by a half-wave square wavelength. You want to calculate the numbers. Next. Yes. What is an antenna? Pattern. An antenna pattern really is a three-dimensional beam shape with gain varying in direction, and the left-hand image there. However, as you know, more likely know that we like to express, we like to use two-dimensional patterns to express gain as a function of elevation, or gain as a function of the azimuth, on the right-hand image there. We can have one way to examine an antenna pattern is to imagine the antenna itself is transmitting. What is the pattern? One way to do that is you can measure if you move off to the horizon and measure the signal strength, and you vary the elevation angles, you can then measure the pattern of an antenna, and that's the image on the right there. And the red lines refer, that means that on that particular antenna, the gain is maximum. Oops, right here. Yeah, the gain is maximum in this direction. And the red lines refer, this is the 3 dB point down here where the power is now half. This is the, if you draw a line from here to here, passes through the 3 dB point. So that basically the beam width is the distance between these 3 dB points. They call it the half power beam width. That's how you define the beam width between the half power points. All right, this is a single dipole at 10 feet. I like to use 10 feet because that's a nice low image. In Florida, basically 10 feet is not a bad height for Jupiter being relatively high. I'm in the northern hemisphere, so oops. Here in the left-hand image, we have the dipole running east-west, and this is the pattern in the east-west direction. It's about a 68-degree beam width between half power points. And the north-south beam width for a single dipole is about 118 degrees between half power points. Now, you notice here at the end of in the east-west pattern, you get a null to the east, you get a null to the west. That's from the endpoints of the dipole. There are nulls off the endpoints of the dipole, I'm trying to say. Okay, that's wonderful. This is a wonderful pattern. If Jupiter is in this beam, that's fine. But if you're in the northern hemisphere, Jupiter typically is always to the south of you, right? So this part of the pattern really is not useful to us. Sorry, over here. This part of the pattern is not useful to us because Jupiter is over here someplace. But suppose Jupiter is over here. What do you do? How do you move the antenna beam? That's what the next slide talks about. Here we go. Since Jupiter is not usually at the zenith, we need a way to steer our antenna beam to where Jupiter is, right? So, say for example, in 2015, get my pointer here. 2015, and let's say you're at 40 degrees north, right there, a little spot right there. The maximum elevation for Jupiter is about 65 degrees. So therefore, you want to point your, if that would be the maximum, so you probably want to point your antenna beam down a little south. But so you need to have a way to point the antenna beam to Jupiter. If it's not a transit, how do you do that? Well, in the Jove array, we have a simple solution. This is why we picked the Jove array to begin with. Start with one dipole, that gives you a beam overhead, and for the sun, with fairly wide beam, but it's adequate for the sun. For Jupiter, we don't have enough. If Jupiter is off to our south, which normally is in the northern hemisphere, we want to point the beam. I just lost my train of thought. Oops. Yeah. Jesus. Sorry, I had a brain freeze.
You point the beam south. You want to point the beam.
Yeah, you want to point the beam south. How do you do that? Okay, we do it two ways. We have a single dipole, we had the second dipole. And to the second dipole, we had a phase cable. Between the addition of the second dipole, you gain 3 dB, and you have a phasing cable, which now allows you to steer the beam toward Jupiter, and you can, by doing so, you can move the beam up and down in elevation, say from 20 to 90 degrees. Okay, here we go. The left-hand image here, if the source is at transit, where your beam is pointing overhead, right? Fairly simple image here. The source is overhead. The wavefront, signal wavefront comes down here, hits both the north and south antenna at the same time, goes through equal lengths of cables, and you wind up with an in-phase signal at the output of the power combiner. Real simple. That's for a transit. But once again, if Jupiter's not there, if it's over at 40 degrees south, how do you get to it? Well, as I said, the simple solution is over here. The wavefront strikes from the source, comes off at an angle from the south. The wavefront strikes the south antenna first, then goes through, and then it hits the north antenna. So you can see there's a delay time or distance involved from the north to the south. They're not in phase. Right here, they're out of phase. So what do? You add another phase cable down here. We call it delta. Now, delta equals D in terms of fractional wavelength or degrees. Then the path length to the output of the combiner and the output would be in phase. And basically, the addition of that phasing cable allows you to steer the beam from up and down in elevation. That's why it's the simplest solution you could ever come up with. There are other antennas that are more directional, but they're more expensive, and they're not as easy to control as the dipole is. Okay. All right. And you've seen this before. This is the Jove dual dipole array transit beams overhead. And here's the pattern. Once again, for the two dipoles, the east-west beam always stays the same because they're always running east-west. Now, if you note from the previous antenna, dipole was about twice as wide. Single dipole, the beam was about twice as wide. Here, with two dipoles, you got the east-west. The north-south image is the beam width is half of what it was before, about half. So you basically, that's where your 3 dB gain comes in, from one antenna to the second. Next. Here we go. Now, for example, we threw in a 90-degree phasing cable. What does that do? Jeez. And my mouth is dry too.
That was my water.
No. So what? I use 90-degree phasing cable for. I like this phasing cable for where I live. I'm at 30-degree latitude in Florida. You add the 90-degree phase cable to the south dipole. That's where Jupiter is to the south, and you will get. Notice that the 90-degree phase cable shifts the beams 30 degrees to an elevation of 60 degrees. Shifts the beams 30 degrees to an elevation of 60 degrees. And the nice thing about this pattern is that the beam width for this pattern is about 60 degrees itself. So the 3 dB point would be transit down to 30-degree elevation. So the center of the beam is 60, the low end is 30, the high end is 90. So that one phasing covers from transit down to 30 degrees. Pretty good. Now, if you need to go lower, you're up in Maine or someplace, you want maybe the beam to go lower. You can't do that entirely by just the phasing cable. You can only go so far down, it won't go any further. You go to the next one here, we compare the same phasing you just saw, 10 feet, 90 degrees up here, still 60 degrees. Now you jack the height up from 10 feet to 15 feet. The beam beam center now goes down to 49 degrees. You've lowered your beam by 11 degrees. So between the combination of phasing cable and antenna height, you can control the position of your beam. Now, if you're up in Alaska, this is just how we put attach the antenna to the dipole. As you know, in the kit we include 3 ferrite beads. Why do we do that? The antenna itself is inherently a balanced device, and the coax that attaches to it, in this case, is inherently an unbalanced device, and so you need to have something that will go from a balanced antenna to an unbalanced coax, and that's what we call the balun, of course. Balun, balanced, unbalanced. We add that there. Two types of baluns you can use. We use the ferrite beads here as one choice, or the choke balun is another choice. Choke balun has it's easy to use. You don't have to have any external stuff, but it adds weight to the center feed. Let's see what else. Oh yeah, to prove this is any antenna, you want to have what is balanced. A balanced antenna must, by definition, must have equal currents in both arms of the dipole. This current should equal this current. So if you want to do a current analysis, the current from the right dipole arm flows down to the center conductor, flows back through the load, back up on the inside of the shield, and here it has two paths. It goes to the one path, the current path will go to the other dipole arm. The second path will be the outside shield. And if that happens, the shield's not a shield anymore. It's now part of the antenna a little bit, so you can get increased noise pickup and loss of efficiency. So the balun will correct that. You add the beads to the outside part of the coax. It suppresses this current to pretty much zero. So now IA equals the current over here, and that's what you want. This current IA equals IB, and now the current IBIC is also equal to IA. So that's what's important. That's why you need the balun. You can use it without the balun, but it won't work as well. And this is the review of the physical connections in the Jove array. And the only point I wish to, I'm going to skip a couple of these things. The only point I wish to emphasize is what I would call dipole phasing. Make sure the center conductor is attached to the same compass side on both dipoles. If it's on the east side here, it should be on the east side here, or if it's on the west side here. You're making the same side. If you cross match, if you flip them, or one's on the east, one's on the west, you're going to throw your beam to the horizon like that. And you add a phasing cable, and you've really messed it up. So.
One more minute.
Okay. And there are other. I'm just skip this. There are other antennas that you can use. Small antennas, you pay a price. You don't get something for nothing. Some of the larger antennas that work well are the Moxon, the Yagi. They do work. They have more gain. They have a narrow beam, but they have a lot of mechanical steering problems. You use a short dipole with loading coils. That works, but it's a little more complex to build. It's shorter, and you have other problems. Yagi, you may be familiar with Yagi. Oops. The Yagi is basically a dipole on a boom, and then you add a reflector, which is longer, and directors, which are ahead of it. Gives you more gain, narrows the beam. It's an option, but they're complex. Here you go. You have to support them up, you have to drive them, and they are expensive. So, of course, if hams have them, can use them, it's no problem. But the average person can't afford to go out and buy them. Example of the Moxon, which is comparable to the Jove array. It's actually about the same gain as the Jove dipole array, but it also has construction problems. A little more complex to build. Zenith, you have to point the whole thing. This here is pointing to the south. If the Moxon is pointing, it's horizontal, it's pointing to the south. You have to support it. And if you want to transit, you have to verticalize the whole thing. And if you want to go in between, then you have to do mechanical construction. So it's a good antenna, and some of our people use them. Nothing wrong with it. It is more complex. That's about it all. I'm not going to. And the bottom line is, dipoles, we think, are the best antennas for Jupiter because they're the least expensive and the most efficient. Feel free to experiment with different antennas, but we think the dipoles are a good starting point. If you have more money, you can go to the more complex antennas. Thank you.